Um, all right, so let's get started. So welcome to the last lecture. So most important reminder, the final exam is Monday, May 1st at 3:30 p.m. So, okay, it's unfortunately not going to be in this room. It's going to be in the BEHS, so auditorium. This is part of the infrastructure of the large tower, the Tower of Terror, as I've been told. So it's not actually in the tower. So if you're coming, let's see, so from in front of the library here and walk past the library further south, you walk towards the tower down here, and that's where you are in this picture, and you want to go down underneath through kind of under this tunnel, and then you see this other building over here. On the map, that's the green building over here. This building is just an auditorium. It's got 400 seats, 399 seats, I guess. So we're all going to be in there, and hopefully enough room to mostly spread out. You come in through the doors underneath this kind of this walkway. The doors are not like huge doors; they're a little bit hard to find. So don't be surprised that they're small doors under here. You walk in, you walk into the big auditorium. Okay, that's 3:30 on Monday, May 1st. It will be in person. I know I made most of this class so you didn't have to be in person for basically the whole thing. The final will be in person. Okay, it's going to be on paper, and you'll be able to bring in one cheat sheet front and back. I want you to make this kind of yourself by hand or typing, kind of creating it, deciding what to put in it. You can use scratch paper and a calculator if you need to. You shouldn't need to do like hard calculations. So I don't think you need a calculator. But if you feel you want one, you're welcome to bring one. The most helpful thing would be maybe you actually compute an answer and you realize, oh, it's a probability, but it's greater than 1. So something must have gone wrong, right? But otherwise, if you kind of do the you get to the right point and you make a calculation error, we'll try not to count off points, okay? So calculation should not be an issue on the final. Okay, we have a couple practice finals. One's linked off the webpage with solutions. Another one I made myself recently. This one has 160 points on it. The final will be 100 points. So that's a little bit more questions than you would see on the final, but they're probably roughly about the kind of scale of difficulty and breadth you'll see on them, but less because you only have 2 hours. You should see how long it takes you to do 100 points on that. And if you do that easily under 2 hours, you should probably be fine. I guess I hope something like the average person takes over an hour, but not much more than an hour. Okay, so I hope timing is not an issue. It's fine if you stay to the last minute. There will be people who stay to the last minute every year. I can promise that. So don't feel ashamed if that's you. That's fine. Some people want to check over everything, and that makes sense. It's a final. Will you provide a solution to your practice exam? I have not had time to yet. I'm hoping to later this week. I'll try and post something, but I haven't done that yet. I hope by the end of the week, I'll be able to do that. It may not be kind of super fancy or anything, but I'll try and do something. Yeah. Yeah, I will hold my office hours on Thursday. It sounds like, and they will be confirmed by TA's posting on Canvas. It sounds like the Wednesday and Friday office hours will also exist still. I've heard from both those TAs, and they were leaning towards doing those as well. But I will plan to have my office hours on Thursday, definitely. I have something at 10, so I won't be able to go past 10, but I might be able to handle slightly earlier than 9. So it's from 9 to 10 usually on Thursday. Yeah, okay. Great. So I think we've already covered everything that we need for the final. The goal of this lecture will be a review of kind of everything again. I hope to be able to go through basically all the key things you need for the semester. But if you have other specific questions or things you want me to go over, please so let me know. Otherwise, I plan just to review everything. Homework, yeah, question. So if you type everything yourself, I'm okay with you making it pretty small. If you just like copy and paste stuff and like microfiche it, okay, you probably all don't know what so microfiche was. It used to be, it was expensive to store old newspapers. So they printed them super tiny, and there you go in the library, and there's this big magnifying machine you could read them at. That's not what I want. Okay, I want you to carefully think through and select and write out what you think should be on there. I think you should be able to probably fit that, if you're careful and thoughtful, onto one side, front and back. That would be kind of sufficient. If you feel you want to go to a smaller font and you want to construct it all yourself, that's fine. That's the exercise I want you to go through. I think that's a good kind of learning exercise, right? So if you create it yourself and it's super small and you can read it, that's fine. Okay, but like the point is not that you just take all the sheets and you make them all super small on the one sheet. I don't want to see stuff like that. Yeah, another question? Or, question one. So I heard two different answers. All right, so homework 6. Was this homework 6 question? I will get to, I want to say a couple other things first before we get to kind of open question season. Okay, homework 7 is due today. Okay, this is the latest I'm officially allowed to make homeworks due. So it's due today. So don't forget that. I'll be around after class if there are more questions. I didn't see if homework 6, did that post on Gradescope or not yet? I don't get no. Okay, it should be ready to post. It should post, the grade should post soon. We have everything in, it's just being checked over. So if you haven't posted yet, it should be posted soon for homework 6. And quiz 13 is still open. Quiz 13 is based on the class, so feedback. Been told I'm supposed to try and get class feedback, so incentivize it. So I'm doing it by, if we get 70% of the class to do class feedback, everyone's going to get 100 on quiz 13. Okay, if we get under 70%, then I'm going to drop quiz 13, and your other grades will be worth more. And so I will remove it from Canvas. And if we get over 85% participation on class feedback, I will allow you to drop a third quiz. Okay, I checked this afternoon, we were at 67%. So that's okay. I think we can get to 70% easily, and probably 85%. Okay, so like remind your classmates, people you know, to do it, and I think we'll get to 85%, which would be great. So okay, we need to write the R code on the final. It'd be fair game to ask very simple questions in R. Okay, not any kind of extensive R code coding, but I might ask you kind of a simple thing, or here's part of one line of R code, fill in something in that R code. Right. Great. Okay. So yeah, so we can do question. Do you have a question on homework 6? Well, on homework, a quick question, homework 7, how to interpret something. Okay. 1B. So I'll take a very quick thing and then we'll move these after class. But what is the question? Okay, let's talk after class. I'm not going to give yes, no question. Yes, no. I'm not going to answer yes, no questions. Is this correct or not? But I'll talk to you after class about that. Yeah, but you should write for each of these. You should write a distribution associated with the null distribution, and then kind of what the H0 hypothesis and what the H1 hypothesis, which is the alternative hypothesis, should be a distribution for the null hypothesis. Okay. Great. So I'm going to try and just review stuff for the semester. All right. So we started with, and I'll probably try and cover a lot. So I will be doing a bunch of writing. So kind of feel free to speak out a little bit in case I don't see your hand. I'll try and look a bit. So we'll start with probability, right? Key thing about class, about this class for the semester, this course. And we started with these events A and B, and these are things that could happen, right? It's not, or they're sets of things that could happen, right? Sets of things that could happen, okay? And we were thinking about that A would be like a subset of a sample space, and the sample space was all things that could happen, okay? And so you could think of so a probability of an event which mapped from a subset of the sample space to a value 0 and 1. So a probability must be between 0 and 1. Okay, we looked at the so conditional. So probability was given between two events, A, so given B, right? So you want probability of A intersection B divided by the probability of, so B, you could think of this as having a full sample space, having an event, so A here, which is interesting, and then think about a event B, okay, and then you want to say, I'm restricting the probability of A given that B is true. So then I have a restricted sample space here, and so I have to divide through by the probability. I'm looking at the intersection of A and B given that B is true. So now afterwards, I only care about this part where A and B are both true at the same time, right? And the probability of being in the what is now kind of purplish, given that I'm in the green area, okay? Okay, another important law is total probability. All right, and if you guys are online, please try and mute. Thank you. So the total probability requires a partition where I say that the sample space is the union of I equals 1 up to so BI. So I've taken some large sample space and I've divided it up into B1, into B2, into B3, and into B4, for instance, and that these BI intersect Bj is the empty set. So these are going to be disjoint from each other. And then I can write that, then I can write the probability of A is equal to the sum of probability of A given I'm restricted to BI times the probability that I'm in this so partition BI. This is a really useful rule to have. So I can say now the probability of a particular event A, I can think of in two parts, right? If this is A here, that first I need to figure out which of the B's I land in. Think of this as this like tree diagram, which of the B's I land in, and then given I was in that section B, what's the probability that I was in A? So it's the probability I land in B times the conditional probability I fall in A, given that I had landed in that, so BI, right? So I can write it as this, so formula. And then we talked about like some tree diagrams as ways of thinking about this. Okay, yeah, let's do a little example of a tree diagram. Okay, we haven't seen these for a few months probably. Might be a good example. So I'm going to do two events. First, I'm going to flip a coin. It's going to be heads or tails. Two, I'm going to roll a die, and I'm going to care either I'm less than or equal to 2. This is the first event, or it's going to be so it's going to be bigger, or let's say greater, which is the set of greater than 2, right? So that's 3, 4, 5, 6. Okay, and so I can think of this in two parts. So let's say I start here. It's either a heads or it's a tails, right? Each of these happens with 1/2. So probability. This is the coin, and then there's the die, and it's either the less than or it's the greater than, less than, greater than. This is the less than is 1/3, greater than is 2/3. Okay, so these are the probabilities I get less than or so greater than. Then I can write, and the probability that I got a tails, and the die was less than or equal to 2, then this is going to be equal to 1/3 times, this is the conditional probability I rolled less than or equal to 2, given that I flipped to tails, times the probability I flipped to tails, right? So I can write this as the probability, that's 1/6. That's probably I got a tails and I was so less than. So I can write this as the, so is this probability? I could then say the probability I got, so probably I got, let's say a heads, and then I, so like rolled, so less than, this is going to be equals to 1/3, 1/3, the conditional probability I rolled less than, given I landed on a head, times 1/2. Right, so this is 1/6. Okay, again, that's the heads and less than. And so then the probability, the total probability, let's say the probability I got less than is then equal to the sum of these. Probability intersection tails and less than, plus probability that I did heads and so less than. And that's 1/6 plus 1/6, and that's going to be 1/3. Okay, it's a pretty simple example. There's not a lot of conditionaling. There's the probabilities are less than or greater than was not conditionally affected by the head flip. So it's a pretty simple example, but it's kind of a simple use of the total probability. Now, this was something that was a little tricky back at the time. So this might be something to review. Okay. Let me say a couple of other useful things about events. Another one important one is independence. Okay, and this is between two events, A and B. And this is if and only if the probability of A given B is equal to probability of A, right? So the probability that an event A happens is independent of probability that B happens if knowing that B is true does not affect the probability of A. So if I condition on B, does not affect the probability of A. It's equivalent to probability of B given A equals the probability of B. And you can also say equivalently the probability of B intersection A, that they both happen. This, if they're independent, this is equivalent to the probability of A times the probability of B. These are all definitions of independent events. Right, and so I think we saw in the statistics part that this one is particularly useful because we're looking at a whole bunch of events from random samples, and we kind of take the product of all these events. That's how we drive these more complicated probability distributions. Okay, and then another critical thing is Bayes' rule. Okay, Bayes' rule is based on conditional probability. Probability of B given A is going to be equal to the probability of A given B times the probability of B divided by the probability of A. So it turns out when you're doing data analysis, this is turns out to be very important. You want to think of B as a model of the world and A as data. And you say, what's the probability of the model of this model of the world given the data that I have observed? And so then you want to find the model that's the highest probability in this way. And so that's what the left-hand side is. And it turns out it's easier to calculate the right-hand side off. So this is a super important rule to use in both statistics. Bayesian statistics is kind of built around studying versions of this rule, and a lot of machine learning and data analysis is derived based on this rule often, because you want to calculate the left-hand side, and often you can only calculate kind of this side over here, and maybe you can often ignore this quantity. Okay, but this is a really important rule, so something I think you should probably learn from the class. Okay, this is the review of probability section. Okay. Okay, then I think things started to get probability. You probably saw most of this before in, say, a discrete math class or something else. What maybe things got a little bit more conceptually challenging when we start talking about these random variables. Okay, and we usually use X for a random variable. And this, confusingly, X is actually like a function from the sample space to like some real values. It doesn't have, it's not an assigned value yet. It's something that might, it's kind of some quantity you might measure in the future. Okay, so, okay, and so we can think of this as a function from omega to the real values. And examples of discrete, examples of like omega would be like, rolls of dice, right? Or flip of coin. And if I do this, then I can write the probability of X equals to, say, of heads, and I can set, there could be some particular outcome, or maybe I need to set this to a real value. So like 1, I say the probability of a particular value happening. Okay, I can say this probability. But if I'm in the, so continuous case, so this would be something like, so rainfall or so time, right? So if you look at quantities that are like rainfall or time, they're not these discrete events where you're counting something or saying it's there or it's not there. You need to have a continuous random variable. And then we needed to say, well, the probability that the rain is, say, less than or equal to, so 1 inch, okay? So now I can talk about the probability of these kind of intervals over the space of the values it can take, okay? And so this is a one-sided interval. It's something less than 1 inch. I guess it can't be negative, so it's probably between 0 and 1, okay? But I can take a probability over an interval of the real values instead, okay? And to define these, we often have a probability, so density, so function, okay? And this is for the, so discrete case, I can say that the f of a would be the probability, maybe for a random variable x, probability that x is exactly equal to a. And then, but for the continuous, so I would say that f, so it's hard to measure so instead I could say the probability that x is in some range between, say, a and b, right? This is equal to the integral of lowercase x equals to a up to b of f of x a of lowercase x, so dx. Okay, so I have to integrate to get the probability for these continuous so random variables. And then you also have the cumulative density function. Okay, and so this would be f of x and of a, and this is always equal to the integral for a equals 0, or so for x equals 0 up to a of f of x a, so dx. So this is the probability that x is less than or equal to a. Okay, so we can, for discrete and continuous random variables, this one is basically always the same. You could replace the integral with the sum if you wanted to for discrete stuff, but you can, if you write an integral, it's not so wrong. So at least not in my book. And some measure theorists might complain about some stuff, but I'd say it's fine. Okay. Important things about random variables. Okay. We can finally talk about expectation. Okay, so this is the kind of like the average. Okay, and I can take the expectation and I'll write the general form for some function of a random variable. The function g might not do anything. It might just return the value of the random variable. But this form is very useful. For discrete, this is going to be sum I equals 1 over all the values it can take, g of ai times f of x ai, right? So it's just this is the sum over all things, the probability. This is equal to the probability that x is equal to ai, and this is the value it takes at that probability. This is the expectation for discrete random variables. For continuous random variables, this becomes an integral over x of g of x, the value it takes, times the density it has at that value, and you have to integrate over this. Okay, so the expectation can be written here. If you understand how to use this rule, you can always calculate expectation of various quantities. This is very general rule for expectation. Okay, and then we can define the variance as well. This is the expected squared deviation. Okay, variance of x, we'll write this as var of x. It's the expectation of x minus the expected value of x squared. Okay, it's important to note that realize this definition. It kind of reminds you that this quantity is not automatically always zero. You cannot factor out the expected value inside because there is a squared term out here, and you can't factor it out through the squared. You can do some expansion and simplification, and it turns out to be equivalent to this expression, where one has the square inside the expectation, one has it outside the expectation. It's the difference of those two. And those are not the same in general, right? Unless they're both zero. So those are not the same. In general, expectation typically has a non-zero value. So you can't factor the squared quantity out of here. These are not, this is not always zero. Okay. Okay, and then let me add a whole slide for the linearity of expectation. Okay, the linearity of expectation, these are really important rules. We'll have x and y are going to be some random variables, and a and b and c will be some constants. And then I'll write down some very useful rules here. The first one is if I write a times x, expectation of a times x plus b times y plus c, okay, I can factor this out as a times the expectation of x plus b times the expectation of y plus c, okay? The constants you can just pull straight out. You can separate things by sums, that's fine. You can factor out the constants in front. If a squared term was in there, you cannot factor that out, right? So if you remember the variance definition, that did not allow you to factor that. So C is a constant, right? So what is the expectation of a constant? I can check by putting that back into this expression up top here. G of x is always going to be the value C for that expression, right? So if I integrate over like this expression here, right, and this is all we see, that means that if this is all we see, then what I can do is I can factor out the C, integration of f of x, so dx, and if f of x is a probability distribution, which means that this term is exactly 1, right, which means that this is just equal to C. Okay, so if you put the expectation of a constant, you can see you always get exactly that constant. Okay, great. So great question. Okay. There's also, you might want to do this for the variance as well. So the variance of ax plus b, okay, what is this going to be? Well, this is going to be a squared times the variance of x. Okay, the a, when you remember the variance was a squared quantity, right? So I factor out the coefficient a, it becomes squared. When I factor out the b, that means how far it changes from the expectation on average, but b goes into the expectation too, so the b just disappears, right? how much variation do I have from the mean? If I add b, I'm shifting the mean, but I'm not changing how much stuff varies from that. So the b just disappears here. That's not a mistake. I've finished writing. Sometimes I'll be writing and then it'll stop showing up on the screen for a few minutes. That hasn't happened here. This is done. Okay, and then one more important thing, the variance of x plus y. Okay, what can we do here? This is equal to the variance of x plus the variance of y. Now, I haven't finished writing yet. In this case, now I need an extra term. Turns out 2 times the covariance of x and y. Okay, so I have to worry if they covary together or not. So it's complicated to factor out if I'm adding together variances of x and y. So I can say if x and y are independent, then the covariance of x and y equals 0, and then I can ignore that other term. So if we have independence, then things are kind of like nice again. But if we don't have independence, then you need to worry about this extra covariance when you're adding random variables for variance. Okay, so these are useful formulas to know. You know, these are, if you have them on your cheat sheet, then if they're on the final exam, then you can apply the formulas, right? Okay, good. All right. Yeah. Yeah, so the variance of a constant. Yeah, so the variance of a constant is always going to be 0, right? If we look back in the formula, let's use this formula here. Let's say that I say the variance of a constant. Okay, so that's going to be the expected value of the constant squared minus the expected value of the constant squared. Okay. Well, turns out constant squared is still a constant, so I can factor this out as c squared times 1, right? And then the expectation of c is exactly c, and so then I square that. Okay, and this is just c squared minus c squared, and this is always 0. Okay, so the variance of a constant is always 0. Okay, good, great. Okay. Okay, good. We okay, then we got into when I was in college learning this stuff, we introduced all these distributions. And I hated, I always liked kind of understanding the derivation of stuff, and the distribution seemed like something you just had to memorize, and I'm like, I don't want to memorize those. But I'm hoping now you've seen that these are really useful in the statistics part, because we can describe these distributions like the Bernoulli, right? So this is x a Bernoulli p, and this kind of parameterizes this kind of nice way of thinking about a modeling of the world, and then we kind of try and learn or estimate or put some uncertainty on these parameters, and that describes this whole kind of modeling of the world. So kind of parameterizing the way we think about the world in these ways kind of really simplifies the thinking and allows us to use these high-powered statistical tools. Okay, and so this is x equals 1 with probability p and 0 with probability 1 minus p. The expected value of x in this case is going to be exactly p, and the variance of x is going to be p times 1 minus p. Okay, so it's useful. There's a nice kind of simple form for the variance if you know the value p here. Okay, so Bernoulli random variable. This is kind of like a coin flip, maybe without a fair coin. All right, p is the probability you might get heads. So binomial, okay, is then going to be, we'll say x binomial Pn, or I guess we typically wrote it as NP. This has two parameters, N, which is the kind of the number of coin flips, and we're going to add up the number of heads. We're going to count the number of heads, where Bernoulli is just one flip. Binomial has multiple flips there. Okay. Okay. So the expectation of the binomial random variable. Oh, let me first say the probability that x is equal to k, which is the number, k is equal to the number, say, of heads. This is equal to this kind of complex expression, n choose k times p to the power k, 1 minus p to the n minus k, right? So that said, we flipped the p to the power k is we flipped it k times and it landed on heads. 1 minus p to the power n minus k is we flipped it n minus k times and it landed on not heads. That's 1 minus p. And then this is all the ways we could do that in various orders, is the n choose k, right? So that's where we get the probability of this happening. Question? Yeah, so I've kind of told you that I've told you that you're not going to have to do any really hard calculations. So if I ask you a question like this, it would be worth a lot of points and you'd have a tough time on it. So probably won't ask it. I probably won't do that. Yeah, so it's good to know what it is. Maybe I say, oh, which of these formulas is the definition of the probability for a binomial distribution? But doing the calculation seems like that's kind of a pain. That's why they wrote the R language, to do this stuff for us, right? You know, understanding what it is, how to interpret it, but how to do the calculation seems like not something that is pressing. It's like, you know, if you had learned this material like 50 years ago, they might say, yep, you need to know how to calculate it. You're going to have to do that for the rest of your life, over and over again, doing the n choose k, might as well memorize it. Now we don't need to do that anymore. Yeah. Is there other hands? Yeah. Yes, the number was, it's the, so it's called the combination. It's, blanking on what I learned in other names for in combinatorics. Typically I call it n choose k, the number of combinations of k things out of them. But it implies the order matters. It counts the number of different orderings you can do over those. Yeah, okay, great. The expected value, some things that are easier to remember, right? That probability is kind of complicated, but it turns out the expected value is pretty simple. It's just n times p. Okay, and the variance is just going to be n times p 1 minus p. Okay, these are all thought to be independent events, so I can just add up the variances. Remember, variances, if they're independent random variables, I can add them up. This binomial is just the addition of a bunch of these, so Bernoulli random variables. Okay, and then there's the geometric. Okay, distribution x geo of p. Okay, this is the number of trials. This is going to be the number of trials until the first, say, so heads. If I've got a coin with heads with probability p, okay, a number of trials until success, again, of a Bernoulli random variable with parameter p. The expectation, again, is the definition of the definition of the probability of x equals k is going to be equal to, again, this is a little bit complicated, 1 minus p to the power k minus 1 times p. Okay, so the pth time, the last time I do it, I finally get heads, and I get, for the first k minus 1 of them, I get, I don't get heads, so it's 1 minus p. Let me, this is k minus 1. Okay, there's a couple of variations on this definition. If we're on the, sometimes you do 1 minus p to the power k is what this means. We will try and be explicitly very clear in the test if we use this, so you know which one we're talking about. Okay, the expected value, again, is pretty easy, 1 over p, and the variance of x equals 1 minus p divided by p squared. Okay, so again, this parameter kind of tells you everything you kind of need to know about the distribution. If you have a bunch of events and you know exactly how many of them, right, then you might say, well, then it has to be binomial, because I know I have exactly n of them. If I know I'm going to have a bunch of events, but I don't know how many, and the first one that matters, then you might say the geometric. If I have a bunch, and I'm kind of doing statistics on them, like confidence intervals or hypothesis testing, probably Bernoulli is kind of a thing to do, because that's a simple model, and I'm going to kind of add these things up. Okay, but if I just have one flip, it's just going to be Bernoulli. Okay. Then we had these continuous distributions as well. The main ones were the uniform between A and B. And this is if X is the, so the f of X equals 1 over B minus A if X is in the interval from A to B, and it's equal to 0. So otherwise, okay, this is the uniform distribution. A and B is kind of uniform over those values. The expected value of X is equal to B minus A divided by 2, and the variance of X is equal to 1 divided by 12, B minus A squared. It's kind of a little weird, but it's kind of a simple formula. Okay. That's how the math works out. So you can plug it into the expectation formula and calculate it, and it turns out to be 12. Yeah, could be a good exercise to work out to test your knowledge of the variance. Okay, the exponential. Okay, this is if X is in the exponential distribution, and this is like a continuous version of the geometric distribution with the rate parameter L. So this is like the amount of time until the light turns off or the projector stops working, right? And so I can define this with f of X equals L times, that's e to the power negative Lx. Okay, and the CDF also has a nice form, which is 1 minus X to the negative L times A. Okay, so it's got kind of this nice form. It's kind of like a decaying function here. So it starts, it's a positive value. So the time kind of is decaying exponentially. The PDF is decaying exponentially as X is getting bigger. Okay, so that's the exponential distribution, and how fast it goes down depends on L. The larger L, the faster it goes down, and you can kind of see this by looking at the expected value of X equals 1 divided by L, right? So the expected value is kind of, you know, this might be the expected value. So the larger L, the faster it goes down, the more frequently it happens. The expected value, the expected time until the light goes off is smaller. The variance of X equals 1 over L squared. Okay. Yeah, you can use something else instead of e to some power, and it's still an exponential distribution, but then the expected value and variance have some other factors in them. So this is why it's nice. Okay, and then finally, one other distribution, probably the most important distribution, the normal distribution, and this is sigma squared. And so this is the PDF is defined for f of x, 1 over square root 2 pi times the sigma times e to the power of negative x minus mu squared divided by 2 sigma squared. Right, so this is all in the exponent. This is the normal distribution. So if we have here, we have the mean. This is x, and then the normal distribution. So this kind of centered around the mean, and then this distance about halfway up going over is about 1 standard deviation. That's sigma out. So sigma squared is the variance, mu is the mean, right? The expected value of the distribution. Again, the things we often want to know about the distribution are easy based on the parameters. That's why we chose those as the parameters of the distribution. Yeah. It does not have a closed form. So you can, if you want to compute the CDF of A, what you would do is you would use R, and you would do, P norm of A, and I think we have to put in parameters of mu and sigma squared in there. And I think the default is going to be if you just do if mu equals 1 and sigma squared, so mu equals 0 and sigma squared equals 1, then this is equal to P norm of just A. Okay, so those are, says the defaults. Okay. Okay, so this is kind of an important distribution. Yeah, you can also write f of x of A as just the integral negative infinity up to A of f of x of x dx. It's defined through its integral if you want to do that. But it's stored in a table inside of R, and computing the integral, there isn't a closed form, so you look up in a table, and that's what that function is. Again, this is why people wrote R, because they were tired of looking up stuff in actual tables in the backs the back of textbooks. It used to be, and this may have even been the case when I was a student. My probability textbook in the back of it had a bunch of tables in it that said, well, if I want to look up the CDF of the normal distribution, well, I go to that table in the back of the book and I scroll down to the value A I want, and there's the value in the table. Right now we have computers to do that for us. Yeah. Yes. The student t distribution is always assumed to have mean 0 and standard deviation 1 are kind of the expected standard deviation 1. And yeah, and so the only degree of freedom is the only other parameter that you pass in other than the A you want to calculate is the degrees of freedom. You only use it after normalizing by the sample variance. And so that sample variance is then folded into the distribution, because that's also has some uncertainty to it. And that's why it's different than the normal distribution. Okay. Let's see. Okay, should we do, I can keep going a bit. We're probably not on pace to finish. I want to go over joint probability, estimation, and then confidence intervals and hypothesis testing. Okay, how about I just kind of do slightly abridged version, keep going, and we'll see where we get.
Okay. Excuse me?
Yep.
Excuse me? What's the symbol under the square root on the previous page?
Under the square root, that's 2 pi. That's this. That's a pi. Well, there. Let me try a less thick. There. Great.
Okay. Thank you.
Okay. Okay, let's do joint probabilities, and I'll do an abridged version of this. Joint probabilities are when you say probability of X equals A and also Y equals B. We'll often see this as like a table where you have 2 random variables, A and B, and they can say take on values like 0 and 1. Okay, and these values in the table should add up to 1. So 0, 3, 0, 1, 0, 2, 0, 4. Okay, and so this is over here, this 0.5 is equal to the probability that B is equal to 1. What I've done is I've added up along the row. This is 0.5 also. Similar, I can add up along the column, 0.4. This is the probability that A is equal to 0. This is 0.6. These are called so marginal probabilities, because I write them in the margin of the table. All right, that's a good way to think about them. Okay, whereas we already talked about the conditional probabilities as opposed to a conditional probability. So the probability of B equals 0 given A equals 1, right? This given A equals 1 corresponds with that column of the table. So I reduce everything there. And we already said, well, this is equal to probability that B is equal to 0 and A is equal to 1 divided by the probability that A is equal to 1, right? Just the law of conditional, so probability. So I divide by 0. So I divide this by, this is 0.6, which I got from here. And then this quantity, B is 0 and A is 1, 0.2. And so this is equal to 0.2 over 0.6, 1/3. Okay, so that's how you can do a conditional probability in a table. Okay, little tricky things about this are that in the dependence, now we did kind of conditional things with the events before, which is what this is, but now we can say independence over random variables. We have 2 random variables now effectively. I switched from X and Y to A and B in the table there, but I have two random variables, A and B, and so random variables, X and Y, are independent if and only if for all choices of A and B, probability of X equals A times probability Y equals B is equal to the probability of X equals A and Y equals B. And now I can read this I can read, say this one, you can read off of the table, okay? And then these two, I can do with the marginal, so probabilities. And this has to hold, it only holds for random variables if we have for all values A and B, for all possible events or all possible outcomes, that this is going to be true. Okay, so that's the key thing to remember about the joint probability with random variables. Quickly, we can talk about expectation. Now I can talk about a function of X and Y, and this equals in the discrete form I and J of G of AI Bj times probability of X equals AI and Y equals Bj. Okay, so it's the same thing as before, but now I have a double sum over all the possible outcomes. I have this joint sample space over the outcomes of X and Y, take on all the AIs and BJs that they can take on, and I need to just sum this over everything. Okay. And then the covariance of X and Y, this is going to be equal to the expectation of X minus expectation of the expectation of X, the difference from EX times the Y times the difference from the expected value of Y. Okay, and this is equivalent to the expected value of X times Y minus the expected value of X times the expected value of Y. Okay, again, remind the fact that the second expression is not always zero should remind you can't factor out X times Y into separate parts. Otherwise, it'll always be zero, which is not always the case. If they are independent, it will be the case. And then it's always zero. So if X and Y are independent, then the covariance of X and Y is equal to zero. But if the covariance of X and Y is equal to zero, then so maybe X and Y so independent, but also so maybe not. Okay, so covariance being zero does not imply independence, and this is kind of useful to keep in mind. Okay, and if covariance is positive, that means that as X gets bigger, Y also gets bigger. If it's negative, it means as X gets bigger, Y gets smaller. Okay. All right, let's talk about expectation. Oh, talk about estimation. Okay, so estimation is to, this is part of, so statistics. So we're going to start with a random sample, X1, X2, up to Xn. And these are IID from some sort of distribution. And the goal is to learn the parameter of, or to make a guess, an educated guess based on the data from the parameter. And these are these are all random variables. These are random variables, which allows us to talk about the probability. We don't actually we do all the work ahead of time thinking about the probability before we go and look at the actual data. So we figure out what we're going to do before we actually look at the data. And our goal is to estimate the parameter, so theta here. It could be the mean of a normal distribution or P in a Bernoulli distribution, right? These are common examples. Okay, what does IID mean? IID is independent and identically so distributed. Okay, so this is a common assumption in statistics and in machine learning that all the random variables, all of our eventual data we're going to collect are from the same distribution. They're identical. That means they're from the same distribution and that they're independent. That means we can apply all these nice rules about the covariance being 0 and the probability, the joint probability is a product of individual probabilities. We get all these nice things to happen because of independence. So we're going to assume all these things so that all the probability works out very nicely. Okay. Okay. And so what we're going to do is we're going to create an estimator, which we'll call theta hat, which will be a function of the random variables. That means that the estimator is itself also a random variable, which means until we actually do the same calculation on data, we can talk about its probability, assuming it came from some nice sort of distribution we want to estimate the parameter of. We can do things like compute its bias of theta hat is going to be the expectation of theta hat minus the actual value of theta, right? We can only calculate talk about the expectation because it's a random variable, where theta is a constant, so we can't talk about its expectation, but we can compare these. The expectation turns that into a constant again. Yeah. Yeah, okay, so that's a good question. The estimator is usually derived from the sample mean. Okay, we're usually going to use the sample mean, and we're going to look at, we often want to look at we would say we'd like an unbiased estimator, right? If it's unbiased, that means that the bias of theta hat is equal to 0. And this also means that the expected value of theta hat is equal to theta, okay? So this is what I want my estimator to do, so I can write down, well, how do I get something that has the right expected value? Well, I start typically by saying, well, xn bar is 1 over n, sum I equals 1 up to n of xi, and I know that the expected value of xn bar is equal to the expected value of xi. And so if the parameter I'm trying to estimate, I know maybe that this is equal to the parameter I'm trying to estimate, right? If that is the p in a Bernoulli distribution, then the expectation is exactly what I want. If it's the mu in a normal distribution, then the expectation is what I want, and that means that the sample mean, which is a random variable, is a good test statistics to use. If I have some other sort of distribution where the parameter is related to the expectation, let's look at these distributions again. In the normal, look at the distribution here, expectation is equal to mu. Great. In the exponential distribution, the expectation is 1 over L. Okay, so I calculate the expectation, maybe I do 1 over that, and I can get to L. In the uniform distribution, expectation is B minus A over 2. If I know A or B, then maybe I can solve for the other one, right? Here, expectation is N times P. If I know P or N, I can solve for the other one. Your homework question had you do something like this, right? Here, it's P. In geometric, it's 1 over P. Okay, so once I get the expected value of X, I can often solve algebraically for a good estimate. Yes, it's a good question. All right. All the questions are good questions. Okay. Okay. Yeah, so the sample mean is kind of a very common distribution. Other one you might want to do is the sample. So variance, this comes up a lot. This is Sn squared. This is 1 over n minus 1 times the sum over the random variables of xi. And this one has the property, this is kind of the other thing we often need Sn squared. The expected value of this turns out to be exactly, so the variance, that was pretty much the only other parameter we had that we talked about that didn't show up as some formula related to the expectation. Okay, so now we have another formula of the sample variance. We proved this in class that this has the expected value of the variance. Okay, so this is kind of a nice thing, nice property to have. Okay, and so this gives an estimator for that. Okay, so this, I could say that this is equal to sigma squared hat. Okay. Confidence intervals. Oh, I wanted, actually, before I go on this, one more important thing I think is important to write down. The central limit theorem. This is about, you have x, x1 through xn, iid, from some distribution, and we want to talk about xn bar. Okay, and there are 3 properties. The first that we already wrote down, xn bar, the expected value, is equal to the expected value of each of the xi's. Let me just write these down. The variance of xn bar is equal to the variance of each xi divided by n. And that if I normalize this, I do xn bar minus the, let's say this is equal to mu, this is equal to sigma squared over n. So then if I normalize this by mu divided by sigma squared over n, this is approximately distributed as the standard normal distribution, as n gets large, as n goes to infinity, for basically any distribution I start with, anything with bounded variance and a known expectation. Yeah. Oh, yes, you're right. I totally messed that up. Yeah, that's the sample variance formula. Okay, check your notes, make sure you wrote that down correctly. Yeah, I got that. Yep. Yep, you're right about that as well. Okay, this is the part of the review where you I make a mistake on purpose, and you're supposed to catch it. All right, good, and all you're doing great. All right, you're the same, caught this one of the same ones. All right, okay, great. Okay, good. This is super useful. This is kind of central to kind of statistics. This is what allows most of this to work, because we're getting better and lower and lower variance as we get more and more data. With the same expectation, things look like the normal distribution. Okay. So confidence intervals. Okay. And okay, a 100, 1 minus alpha % confidence interval, okay, is going to be defined by L and R such that the probability that L is less than theta is less than R, less than or less than equal than, doesn't matter. These are continuous random variables. This would be exactly 1 minus alpha. Okay, so that's saying that the probability that the parameter you're trying to estimate is inside these bounds L and R is exactly 1 minus alpha. That means there's a alpha probability that the thing you're trying to estimate is outside your interval. Okay, and you want, say, alpha to be like 5% or 1%. You're saying 1% of the time, 5% of the time, it's okay if I'm outside the interval, but this is a pretty good guess. Okay, L and R are random, so variables, okay, that are kind of from the random, so sample, okay, and theta is an unknown, so parameter, right? So that's the unknown parameter. It's a constant of the distribution. So the randomness and the probability is an L and R, okay? And we typically, how we often do this is we create a Z random variable, which is going to be this normalized X bar N minus mu, which is the expected value divided by sigma square root n. And remember, this is approximately from the normal distribution. So this is if xi is, each xi is from sigma squared. So if we know it's from the normal distribution, we get exactly that. It's also that kind of in the limit with enough data. And then we calculate some delta n, which is equal to this Z value of alpha over 2 times sigma over square root n. This might be called the margin of error. Okay, and then we say that L equals X bar n plus delta n, and R equals X bar n. Oh, I got these backwards. L minus is the lower bound, so it's minus delta n, and the larger side of the interval is plus delta n. Both x n bar and delta n are, no, delta n is not a random variable, that's a constant in this case, but if you have to estimate the variance, then this is going to be a random variable as well. Okay, and Z alpha is, yeah, and Z alpha over 2 equals in R, this is an R command of 1 minus alpha over 2. Okay, and what we get in the end is that the probability of Z alpha over 2 is less than or equal to mu. This is okay, so we have that this Z random variable, Z is a random variable, but the lowercase, the uppercase z is a random variable. The lowercase z's are these values we've read off of this table in kind of the inverse table. This is the quantile, and this is the probability over z here. And if instead we can do some algebra and solve for mu, this is equivalent to the probability that ln is less than mu is less than Rn. This is 1 minus alpha. Okay, so these are equivalent to each other. I do this equivalency by either putting L and R, doing those by kind of adding this delta on either side, or I can normalize the random variable here. Okay, if each xi is from a normal distribution sigma squared and sigma squared is known, right? And I realize this after 5. I'll keep going. I think I've got about 10 to 15 minutes left. You're welcome to stay or not. I won't be offended. I figure I'll just wrap up the review. Okay, so if x is from an unknown, has an unknown variance, or say, or alternately, xi is from a Bernoulli distribution P. Now I also, because I'm trying to estimate P and the variance is P times 1 minus P, then I also don't know the variance. So then I need to calculate the sample, so variance, right? So this is Sn squared. And remember, this is either the 1 over n minus 1 sum of xi minus xn bar squared, or in the case of the Bernoulli, this is just p 1 minus p. Okay, and those are my estimates. So this is equal to, I'm estimate xn bar is an estimate of p, right? So this is going to be xn bar 1 minus xn bar. Okay, and so this will give me a sample variance. And now I need to create a t random variable. This will be xn bar minus mu divided by the sample standard deviation divided by so square root n. Okay, and I don't know what mu is, so but this is from a t distribution where the degrees of freedom are equal to n minus 1. I know this is from a t distribution, but I don't know what mu is. So now I can solve for delta n is going to be then it's going to be t alpha over 2 times Sn divided by square root n, where t alpha over 2 is going to be written in R code as qt with 1 minus alpha over 2 with degrees of freedom equals n minus 1. Okay, and I can get a confidence interval where L equals xn bar minus delta n, and R equals xn bar plus delta n. Okay, these are now random variables, and I can ultimately get that the probability that Ln is less than mu is less than Rn, or ln R, is equal to 1 minus alpha. Okay, so this allows me to get a confidence interval for the mean, and the L and the Rn are random. And this is if I didn't know the variance, I folded this into my random variables, L and R, and I had to change how I got the quantile values now from the t distribution instead of the normal distribution. Yep. Well, so you'll notice there's another n-1 that goes into the degrees of freedom. So it kind of is saying what's happening is that I've got all these random variables, but I also know that the sum of them is exactly xn bar. And it turns out that this adds a constraint onto the optimization, and I divide by 1 minus n, that makes it unbalanced. And we did that calculation at some point in the semester. Okay, that this makes an unbiased estimate of the variance if I use 1 over n minus 1. So right, so that goes. That's still from the central limit theorem, that the variance goes down at a rate of 1 over n, and so the standard deviation goes down at a rate of 1 over square root n. That's still the case. Yeah. For n equals big, these differences like bigger than like 50 or 100. It's the difference is like quite small. Yeah, and if it was like 10, it could matter. Okay, last thing, hypothesis tests. Hypothesis testing. Okay. Okay, so you want to have there are two things you want. One is the null. So distribution, this is H0. This is like the boring thing, or the so the status quo. And you use this to model where x1 up to xn are coming from H0. So they're coming from the null distribution. So in order to calculate probabilities, I need to have like a probability distribution, and that's what the null distribution is. So this has to be an actual distribution. And then you also have the alternative. So hypothesis. This is H1, and this is kind of a guess of how H0 is so broken. You're saying the status quo is not right. I'm going to collect new data and show you that this is wrong, right? So then I make some bold claim like H0, mu equals 10, and H1, I'm going to say that's totally wrong. Instead, this parameter mu might be larger than 10. I'm not going to say how much larger. I'm just say it's larger, right? And so your null distribution is usually a precise value, and the alternative is where it's different from that precise value. Then the null one, I can actually build a distribution. You often would also say, well, it's from a normal distribution with that parameter 10. So this is precisely, say, and maybe or maybe I don't know what the standard deviation. So that would often be part of the null distribution. Other resources that might do this slightly differently, I think this is kind of simple, nice way to think about it. Okay, and so, and then if you don't know sigma squared, then you need to go to a t distribution, and so you do this as t equals xn bar minus mu divided by Sn squared, and where again, we don't know what mu is, but we're going to algebraically isolate it. But we have to use the sample standard deviation. Okay. Okay, and this will often be our test statistic that we're going to use. This is a random variable. I have all my, and I can do this, actually, because I assume from the null distribution that, right, I can actually take this guess here and plug this down into here, right? So I don't have to go and only do the confidence intervals, put all the random variables there. I can actually build a test statistic entirely here because I assume I know what mu is, so I can get this as a test statistic. I can plug in this is equal to 10. Okay, so that's the kind of the difference between hypothesis testing and confidence intervals. Here, I can plug in a guess of what is mu, and then I can say, oh, how likely is that guess to be true? Well, I calculate the test statistic, and then I want to calculate a critical value. So for a critical value is then going to be T alpha, often QT if I use the T distribution, 1 minus alpha, where the degrees of freedom equals n minus 1. And so then I can say that the probability of T is less than T alpha is exactly 1 minus alpha. Okay, so again, I assume there's some distribution of the data, or of the T distribution. This would be a T distribution. I assume this is mu. This is from the null hypothesis. And then a critical value, this would be T alpha. And so then the probability that T is from this T distribution, right? So then the probability that it's greater that then T alpha value, this is the probability that T is greater than T alpha, which should be exactly equal to alpha. Okay, so then I say if T, this is lowercase, this is the realization of so the data. So if T is greater than T alpha, then I'm going to reject the null, so hypothesis. Okay, and let's say if T is less than T alpha, then I'm going to not reject the null. So not reject the null hypothesis. It's a double negative on purpose, right? So this is a double negative on purpose. It's not meant to be kind of hard to understand with double negative. It's meant to be inconclusive. It's kind of, well, it's not true. So it might be true, but I can't reject it. So it might be true, but I can't totally confirm it either. Yeah. Yeah, right. So the little t, great question here. This little t is a constant from real data. These are from lowercase x1 up to lowercase xn, right? And so I'm going to calculate the test statistic on the actual data, and I get lowercase t. Whereas this guy, this is a random variable. I want to talk about probability, so I have to talk about the process that I could run before I collect the data to understand the probability. Then I can set a threshold T alpha, go collect the data, and then check. So you kind of come up with an algorithm for t, right? Remember this, we would say as a function of x1 up through xn, right? And this function is not just computing the mean, the sample mean, which is xn bar, but it also needs to calculate Sn, which is the sample variance, right? So this t statistic is a function of the random variables. So I also do lowercase t of this, where I have lowercase xn. So when I get the real data here, these are the real, so data, and this is the realized test statistic. Okay, so the lowercase is when I realize it on real data. The uppercase is the random variable. Okay, so random variable I can think about, talk about probability, and we can apply all the tools that we summarized so rapidly today. And then T is what you do in R when you actually get a list, file of data points, and you actually run it through the algorithm and it gets out a constant value. That's a constant, right? So this is a constant. I can't talk about the probability of a constant. The probability that lowercase t is equal to 7.43 is either 0 or 1. It either is that or it's not that. There's no real interesting probability about it. Uppercase t, it's a random variable. I can talk about the probability under this null distribution, which I'm modeling the data as. I said, let's assume this null distribution, this status quo, model the data. If that null distribution was true, what would be the probability I got something that large? That would be, you know, at what point is too large to be realistic under this model? That is the critical value, T alpha. That T alpha is the boundary between large but not so unnormal, between too large, I don't believe that distribution anymore, I'm going to reject it. Okay, and then so I can model this all in the random variables, and then finally I put my data in and I get one particular spot I get. And then I make a decision, either to reject the null hypothesis or not reject the null hypothesis. So if you, so I don't have the R preloaded up here, but there is, so there are a couple we wrote down, right? So if I get, so if I have actual, so data, x1 up through xn, the first thing I do is I calculate the realization of the sample mean. That's 1 over n of lowercase xi. Then I take the realization, so this should be lowercase sn squared. That's 1 over n minus 1 I of xi, lowercase xi, and this guy comes from here. Then I calculate the test statistic t, which is going to be xn bar minus mu 0. This is from the h0 mu 0 equals to some, let's say 10. Okay, and then I divide by the sample standard deviation divided by square root n. Okay, so I could do these calculations directly in R step by step, or I can run like t-test. I could just put the data in, and there's one command which I'm blanking on what that one command is, and it will do all this for you. Right, and then I need to get the T alpha I can calculate independent of that. The T alpha is always going to be QT of 1 minus alpha times the degree of freedom equals n minus 1. So this is an R command. Right, but you could do these step by step in R, or you do this as one, command. You can forget exactly what the command is off the top of my head, but you put in alpha, You put in your data, and it puts this out for you. Yeah. Yep. If you okay, so the question is if your data comes from a distribution that's not normal, but you're probably trying to estimate, probably one of those parameters is either you're estimating or is hypothesized, and you're trying to have an alternative hypothesis for it. Maybe another one, maybe the variance is known to you, but often the variance, unless you're the normal distribution, the variance and the expected value are often so coupled together. And so in that case, you probably need to use a t-distribution. You can still use this general procedure because the central limit theorem tells you that for basically any distribution, as n gets big enough, it will look kind of like a normal. And that means that if I plug in a sample variance instead of the true variance here, it'll look kind of like a t-distribution. So I can always kind of use a t-distribution if I don't know the variance. If I happen to know the variance, then I can plug in, I can use the normal. Well, if we know A and B, we also know the expected value. We know the variance. There's nothing left to estimate or to test. But we may have so the question is, if we're using a uniform distribution and we know A and B, well, then there's nothing left for us to test about it. But maybe we know it's uniform, but we don't know what uniform distribution. So one question is, can you estimate A, or can you estimate B, or can you just say, I just want to estimate the expected value, the average of it. If you know the average and the variance, you can, and you know it's uniform, you can drive A and B. So you could estimate kind of any of those quantities with a estimator. You could put a confidence interval around the parameters you're trying to estimate. Or you could say, well, I've been told it's this value, but I think maybe it's bigger than that. And so then you do a hypothesis test. Yeah, so from a hypothesis test, then you'd have to pick, you'd be given, say, here's a null hypothesis about what the parameters are. And then you say, I have a reason to believe, a hypothesis, that it's different than that in some direction, right? And then you could try and, so you would, again, relate it by the definition of the uniform distribution to, here we go. You would have to use a t because if any one of the parameters you don't know, if you aren't sure about, then you don't really know the variance, right? So then you pretty much need to use the t-distribution. Well, no, actually, I mean, if you're given A and B under the null hypothesis, then you don't need the t-distribution. You can use the normal distribution if you think your sample size is large enough. There are probably, I'm sure it's been derived how to get the exact kind of appropriate quantile for the uniform distribution. Statisticians will say, well, it's not exactly the normal distribution. If I average them together, it's something else, and they'll derive the exact thing. But in practice, the normal distribution works pretty well after you get above, say, n equals 20 or 50, something like that. Okay, I see other hands. There's a question on Zoom that's been there. Will we need to have the Z table or any other tables on the final? No. Is there a late window for homework 7? Yes, the late window on homework 7 is open. Be kind of flexible on that. So if life is crazy, you can ask, but try and turn in by the deadline. Okay. Couple other questions. Or in the context of the statistics? Yeah. Start to speed up around here someplace. So it got a little, okay, yep. Correct. So so this I was talking about confidence intervals, and there we're trying to estimate P and get some bounds on where P are, and then I don't really know the variance because I'm estimating P in the what? This example was under confidence intervals where P is the thing I'm estimating, right? Okay, but for hypothesis tests, if I was given a Bernoulli distribution, then I would have the exact value of the variance, and then I can plug in the normal the normal approximation in the hypothesis test. Yeah. Yeah. Yeah, so the question is, what's the difference between using the t distribution versus the normal distribution? There's one big difference, right? The big difference is when I'm using the normal distribution, I can use the z alpha calculate using the normal distribution, whereas in the t distribution, I need to use the T alpha instead, and that comes from the quantiles of the T distribution. So that's the main difference. There's a secondary difference which is more so subtle. That is, and there was a student asked me about this on Canvas, so I had some discussion on there. That is, this is now a random variable. So when I do confidence intervals, I need to put all the randomness in the ln and the rn. I cannot have my value I'm going to calculate the parameter. Yes, this is over a parameter. But yeah, so in the confidence intervals, you're always bounding a parameter. So all the random variables are in the ln and the rn. But in the hypothesis test, I might say, well, I want my test statistic to just be, I might think I just want it to be xn bar, right? And then I can try and translate, I can do some algebra and move this part onto the critical value. Okay, I can try and move this onto the critical value. Now, that's not right with I use a t distribution, because the Sn is a random variable, and that T alpha value, that critical value, is a constant value. So, but with the normal distribution, I can do that. So if I know the variance, I can actually say, well, my test statistic is just going to be xn bar, and then I can calculate the critical value in the kind of the units that the mean is, and that's a little bit easier to understand. So with the t-distribution, I can't like write it that way because I need that critical value to be a constant. So it's kind of a subtle difference, but yeah, so that's a secondary difference between them. Yeah, great. Yeah. But for a left scale, you would have to subtract the normal part of the less than the value. Yeah, right. Yeah, in this class, for simplicity, I just talked about right-tailed hypothesis testing. You can do it with left-tail hypothesis testing. You need to change a few things, but it works basically the same way. Yeah, but I've told you I won't ask you about that. It's just some extra trick. I'm sure you guys could figure it out if you wanted to. Okay, great.